Welcome to another edition of the emerging topics in biomolecular NMR, biomolecular magnetic resonance, organized by Lohn Andreas, Stefan Glöckler, myself, Oskar Millet, Mei Hong, Art Palmer, and Markus Zweckstetter. We aim to present frontier research in magnetic resonance. Please don't record. No private audio or video is allowed. And we are actually recording the lectures and put them then also on the ICMRVS YouTube channel. Please type in your questions and answers, or in the informal session, which is following after the talks and the formal discussions, raise your hand, and then we allow you on the panel. I'd like also to mention the ICMRVS ECR thing, although I could not find a new announcement, so I just advertised that everybody knows that this is existing. So with that, I hand over to Lucio, who's introducing Daniel, who's replacing Michal.
Thank you, Christian. Indeed, I think Michal is supposed to give a talk at this moment, but she's not feeling well. We wish her a speedy recovery. And in her stead, Jardon-Alvarez at the last minute agreed to give a presentation here. Daniel received his bachelor and master in chemistry from Ludwig Maximilian University in München. He did his PhD with Tito Ponagamba at the University of Sao Paulo in spectroscopy and relaxometry of polymers. Then he went on to do a first postdoc with Philip Grandinetti at Ohio State University, developing new methods in spin 1/2 and quadrupolar solid state NMR. Since 2019, he has been in the group of Professor Michal Leskes at the Weizmann Institute, and he's going to be presenting his work with her on a dynamic nuclear polarization, paramagnetic materials, relaxation, and what's in between. Daniel, floor is all yours.
Okay, thank you very much, Lucio. I'll start sharing my screen. Okay, so thanks, Lucio, and thanks the organizer for giving us the opportunity to talk a bit about our research here. As you can see from the title, from paramagnetic relaxation enhancement to DNP and inorganic solids, we are a group that does not work with biological materials, but nonetheless, I hope that some of the concepts in magnetic resonance that I'm going to present today are going to be interesting for you and relevant for your research. So let me start by introducing a little bit our group. So we are mainly interested in functional materials, and mainly materials that have applications for energy storage and energy conversion applications. And what we want to do is we want to understand how the structure of the material affects ultimately its functionality. And in the materials community, it is well known that introducing small perturbations such as like doping or defect sites or vacancies can really affect the functionality of a material. So if we want to understand their properties, we really need to pinpoint these little perturbations. And you can imagine that NMR is an ideal tool to do this, as it can give us information in the local atomic scale. However, if these perturbations are scarce and rare in the material, we suffer a lot from low sensitivity to the point that sometimes we cannot even detect them with NMR. So our group has been focusing on introducing the DNP methodology to increase the sensitivity and ultimately gain information about the structure of these materials. So most groups that work on inorganic materials and apply DNP on them work and use the following approach. So they soak their sample of interest in the so-called DNP juice, which contains some organic radicals, which then upon microwave irradiation can transfer the polarization of these unpaired electrons to the protonuclear nearby, and then through proton-proton spin diffusion, the hyperpolarization is transferred to the surface of the sample. And this approach, however, suffers from a limitation, which is that most of the enhancement will be limited to the first surface layers. And if we are interested in deeper layers beyond the first of the surface, or even if we're interested in bulk properties of the material, this type of DNP approach will not bring us much forward. So instead of that, our group has been focusing on a fundamentally different approach, which consists in introducing the source of polarization directly into the bulk of the samples. And we do this by doping our inorganic crystals with paramagnetic metal ions, which then, upon microwave irradiation, can transfer the polarization to nearby nuclei. And over the last few years, our group has really made a lot of effort to demonstrate the feasibility and the versatility of this approach by doping a series of different samples with various paramagnetic metal ions. Most prominent are iron 3+, gadolinium 3+, and manganese 2. And with that, we were able to get large enhancement on a series of different nuclei. I want to show you two short examples of what are the type of research questions that we try to address with this approach. So for example, in this study here, we looked at this yttrium-doped ceria, which is an oxygen ion conductor, and therefore it's used as solid electrolyte in fuel cells. And we doped this material with gadolinium 3+. And with that, we were able to obtain DNP enhancement of the yttrium-89 NMR signal, with getting a signal enhancement of a factor of almost 200. And this gain in sensitivity allowed us to do two-dimensional yttrium-yttrium correlation spectra, which is extremely challenging due to the very low gyromagnetic ratio of yttrium. And once we had this two-dimensional maps, we were actually able to say something about the oxygen vacancy distribution, this structure, which is very relevant for its ionic conductivity properties. And another example, Shira in our group worked on characterizing coatings of different particles. So the idea here is for adding a coating on a particle can be very important for lithium-ion batteries. And in this study, she combined the endogenous metal ion DNP approach with the endogenous. And by doing measurements with these two different approaches, she was able to characterize the coating from the inside out and from the outside in. And this way, we were able to obtain chemical information or information about the chemistry of these coatings. And not only that, we were also able to get compositional gradients within this coating. So today I want to talk a little bit more general, like how does this metal ion DNP approach actually works? So as I told you before, in the exogenous DNP approach, we rely on proton homonuclear dipole couplings to transfer the polarization throughout the volume. But in most of our inorganic crystals, homonuclear dipole couplings are very weak because either the nuclei are low abundant or they have low gyromagnetic ratio. So the questions that we were asking ourselves at the beginning is, how does the polarization spread throughout the sample? Or we also wanted to know if we're going to be very localized in enhancing nuclei that are only nearby, or in general, like how the polarization spreads through the sample. So in order to answer this question, we need to look at the relevant interactions for this DNP process. So the most important interaction is the dipole coupling between the unpaired electron, the metal ion that we introduced, and the nucleus of interest that we are going to hyperpolarize. And the dipole coupling, of course, depends on the distance to the power of 3, or the inverse of the distance to the power of 3. So the farther away a nucleus is from the metal ion, the weaker the dipole coupling, and consequently, the less efficient will be the polarization. But at the same time, we have to keep in mind that in this rigid inorganic solids, relaxation times can be very, very long, to a point where the metal ions that we introduce for DNP purposes are at the same time the main source of relaxation. So if this is the case, the longitudinal relaxation of the nuclei will also depend on the distance to the metal ion, since the relaxation time depends on the strength of the dipolar coupling. So the further away we are from the metal ion, the more time we have to hyperpolarize the nuclei before they try to get back to Boltzmann equilibrium. So, and it turns out that these two effects perfectly cancel each other, meaning that the DNP enhancement is actually completely independent of the strength of the dipolar coupling, as long as the paramagnetic relaxation enhancement is the main source of relaxation. And this result has huge consequences for us, because it ultimately means that we are able to hyperpolarize the entire volume of the sample in a homogeneous way, and therefore we will be able to continue getting quantitative spectra. And this all without the need of spin diffusion. And this is the reason, this is the explanation why we are able to get such large enhancement for nuclei such as oxygen-17 at natural abundance. So let me look at another example of a sample that we measured. So in this case, we looked at lithium titanium oxide, which is a material that can be used as anode in lithium-ion batteries. And we doped the sample with different amounts of iron 3+, which is paramagnetic in nature. And with this, we were able to get oxygen-17 natural abundance spectra in just a few scans. So a question that we were asking ourselves is, what would be an optimum concentration of metal ions for DMP purposes? And based on what I just told you in the previous slide, actually the concentration does not affect the DMP enhancement, since the enhancement is independent of the distance. And that's exactly what we observed. So over here is the enhancement of the oxygen-17 versus the concentration of iron. And we see that over a very large range of concentration, almost an order of magnitude of mole fraction of iron 3, the DMP enhancement stays more or less constant. And this is just because the enhancement is independent of the distance. Of course, when we increase the concentration, the build-up time will be shorter and shorter. And however, this distance independency phase on both sides of this figure, and the reason for that is that at low concentrations, at some point the intrinsic nuclear relaxation time starts kicking in. So very, very remote oxygen-17 nuclei from the paramagnetic center start relaxing due to their intrinsic nuclear relaxation mechanism, and therefore they cannot be enhanced as efficiently. And on the high concentration side, the electron-electron interaction starts becoming stronger and stronger, and therefore the electron relaxation time drops, and the DMP enhancement will be less efficient. So back to the question, what is the optimum concentration for sensitivity gains? So from this figure alone, one would think, okay, we want to be at the highest possible concentration before we drop here due to reduced electron relaxation time. However, this figure does not show another important aspect that we have to keep in mind, which is the signal quenching. So due to the strong paramagnetic relaxation enhancement that we have, as we increase the amount of metal ions, we're getting shorter and shorter T2, to a point that some nuclei that are very close to the paramagnetic center we cannot longer observe them due to the instrumental limitation of our dead times after the pulse. And this quenching, so here it's showing the signal intensity, the total intensity relative to the moles of mass that we put into the rotor as a function of the concentration. So it drops as we increase the concentration. So at this point, we wanted to understand this whole effect of quenching a little bit more in detail. Especially, there was one question that really bugged us, which was that if we look at our quenching figures, so how the signal gets quenched as a function of the manganese concentration or iron or manganese concentration, and we extrapolate this curve, we would expect that at very high concentrations for very paramagnetic samples, we would not get any signal at all. However, it is well known that it is possible to measure NMR spectra in highly paramagnetic samples. So we are actually able to, it is actually possible to observe all nuclei in a fully paramagnetic sample. So here are a few examples from the group of Claire Gray. So the question was, how can we connect these two figures here? And the answer to this is the electron relaxation time is changing, or to be more general, the fluctuations of the magnetic moment of the electrons that we put in. It can be relaxation, but it can be also coherent effects that make it fluctuate. And I'm gonna talk in a minute how this parameter affects or explains this behavior. But before that, I want to really emphasize how important this parameter is, because if the electron relaxation time is determining at the end of the day how much signal we can observe, how much is quenched, it determines our DMP efficiency, and it also determines the shape of the NMR spectrum that we measure, line broadenings and shifts and so on and so forth. So it would be really important for us to be able to determine this parameter. So in principle, we could measure electron relaxation times with EPR. However, this can be very challenging, especially in the conditions that we are interested in, that we are doing NMR, like 100 Kelvin or above and high magnetic fields. So what we try to do is ask ourselves if we are able to determine this parameter just from the paramagnetic relaxation enhancement itself. And if we are able to do this, can we use this parameter, the tau1e or T1e, to understand and rationalize the NMR response that we obtain, and eventually even predict DMP enhancements? So I'm going to try to answer this question in the next few slides. And before I go that, let me start with the basic of paramagnetic relaxation enhancement. So longitudinal relaxation and PRE is given by this equation here, which depends on the strength of the interactions, the dipole coupling strength squared, times the spectral density at the Larmor frequency of the nucleus. And now the interesting part here is that the correlation time of the spectral density function is because this is a rigid sample, there are not significantly strong motions, is the electron relaxation time, or the fluctuation of the magnetic moment of the electron. And then the transfer relaxation time has an additional term which is proportional to the spectral density at zero frequency. So now if we plot these two equations, so the relaxation time versus the correlation time, we get the well-known VPP figures, where T1 passes through a minimum and then grows, while T2 keeps decreasing with increasing correlation time. And now here the blue and red curves are the same equations here with two different dipole coupling strengths. So the red one has stronger dipole coupling. And if we look at these two curves carefully, what we observe is actually that for a given correlation time, the ratio between T1 and T2 is completely independent of the strength of the dipole coupling, the strength of the interaction. So, and it only depends on the correlation time. We can show this also mathematically just by dividing one equation by the other, and we see that with this approach, we are able to obtain the electron relaxation time just from the T1 and T2 values, just from the ratio of them, and the nuclear Larmor frequency. But this is a quantity that of course we know. So in the next slides, we're gonna use this equation as a tool to try to understand the NMR spectra that we observe. So the initial question that I asked before was, how does the concentration of paramagnetic species affect our NMR signal? And to answer this question, we prepared a series of samples. So based on this chemical structure, this lithium magnesium manganese phosphate, and we replaced this diamagnetic magnesium with manganese. And the nice thing about this structure is that we can do this from 0% to 100% without changing the crystal structure of the material. And once we had the samples, we did a lot of NMR measurements. And here are shown some spectra. So they are very rich in information. So because they depend on Fermi contact shifts, dipole couplings, and paramagnetic relaxation enhancement. But today I want to focus on one particular aspect of the spectra, which is the signal quenching and the paramagnetic relaxation enhancement. So let's look at the signal quenching. So here is for the lithium-6, which is kind of the cleanest nucleus of that I showed you before. We quantified the signal intensity as a function of the moles of sample that we have in the rotor, and we see that the signal intensity drops with increasing concentration, same as I was showing before. And however, if we keep growing with intensity of paramagnetic center, at some point this trend inverts and we start seeing more and more lithium nuclei again, until at some point at this high concentration, we are able to virtually see all nuclei again. And if we want to understand now this figure, we can look at the relaxation behavior of these samples. So here are in red the T1 relaxation and in blue the T2 relaxation time for these same concentrations. So let me split this figure into three parts. So in the first part, at this low concentration regime, the T1 and T2 relaxation times drop very dramatically. Note that here the y-axis is a logarithmic scale, but the ratio between T1 and T2 stays constant, meaning that the electron relaxation time stays constant. And now we think about quenching as in the following way. Each paramagnetic center has a quenching sphere around it. So nuclei within this quenching sphere cannot be observed because their T2 relaxation time is just too short. So as we increase the concentration, we're just increasing the volume of quenched nuclei until we reach this section B. And at this point, you can see that the ratio between T1 and T2 starts shrinking. So this means that the electron-electron interactions make the fluctuations of the magnetic moments of the electron faster and faster. And what happens because of this is that the relaxation time starts increasing at some point. So we revert the trend. And you can see that, for example, here, T2 is increasing, although we are increasing the amount of paramagnetic center. And at some point, this also happens for T1 until we reach here the extreme narrowing regime. And at this point, we cannot say anything anymore about the correlation time. But how does this affect the quenching? Of course, if the T2 increases, this basically means that the radius of the quenching sphere is decreasing. And this is we try to show it here graphically. So with increasing concentration, at some point, the faster electron relaxation time shrinks the quenching sphere until at some point it is so small that we are being able to detect lithium that are sitting next to a paramagnetic center. Okay, so we can take this even a step further, and using the equation I presented before, we can try to estimate electron fluctuation rates or times. And so just by plugging in the values here for T1 over T2, we are able to get electron relaxation times, which are in the order of 1 microseconds at this very low concentration. And as we increase the concentration, they rapidly decrease below 1 nanosecond. And it would be nice to validate this type of measurements. And so we try to do EPR relaxation measurements. So for that, we went to high field in Florida, at Tallahassee, and measured the electron relaxation time up to a temperature of 100 Kelvin. Above that, the relaxation times becomes too short to be able to measure. And we obtained at this 100 Kelvin for one of the lowest manganese contents, relaxation time of about 3 microseconds, which if we extrapolate it to 300 Kelvin, shows us that we are at least in the right order of magnitude to estimate electron relaxation times just from the ratio of T1 over T2. And then the next question that we were hoping to answer is, can we with this predict DNP enhancement? So we took some of these samples and put it in our DNP spectrometer at 100 Kelvin and tried to hyperpolarize in the lithium-6 NMR signal. And fair enough, we see that at this low concentrations, we get a decent enhancement of 11. And as we increase the concentration with decreasing electron relaxation time, we also decrease the DNP enhancement. So this, at least qualitatively, is consistent and is what we would expect, right? But we wanted to see if we can get a little bit more quantitative into this approach. And for that, the starting point of 11 seemed to be not enough enhancement to do a more quantitative study. So for that, we went back to another sample, so back to the lithium titanium oxide that I presented already before, which we doped with iron 3+. And here, even for lithium-6, we are also able to get large enhancement of above 100. So we took one of these samples, some iron concentration of 0.01 moles, and measured the DNP enhancement as a function of the temperature at which we were performing the measurement. And we saw the enhancement was decaying with a square dependence of the temperature. And at the same time, we were monitoring the nuclear T1 and T2 relaxation times. And here are plotted the T1 over T2 ratio. And with these values, we then can compute the electron relaxation time. And if we plot the DNP enhancement versus the electron relaxation time, we found actually a very nice linear relation. So what this result is telling us is that just by measuring the ratio of T1 over T2, we have a really powerful tool to predict, or at least to estimate to some extent, DNP enhancements at field and temperatures of interest. Okay, so with that, I would like to summarize this work. So I hope I was able to convince you that we can use this metal ion DNP approach to get some interesting information for material science. That this approach is particularly appealing for systems where the intrinsic nuclear relaxation times are very long, because in this case, the DMP enhancement can become independent of the distance, and therefore we get homogeneous enhancements. And finally, I hope I was able to convince you that using T1, measuring T1 and T2 relaxation time, we can get very useful information about the properties of the electron spin and how these affect the NMR spectra and the DMP efficiency. And with that, I would like to thank all my colleagues and most importantly, my PI, Michal, and of course, all of you for listening. Thank you.
Thank you, Daniel. Yes, so I guess I understand that the floor is open for questions and discussions. If
questions should be entered in the questions and answers. But presently, I don't see any. So, Lucio, do you start maybe with a few questions?
Sure. You know, there were two things that I mean, I have the advantage that I think I've heard some of this before. It's a lot to digest, so it's very interesting. I had a couple of questions. One was when you, of course, the main take-home message is this flatness of the DMP enhancement, regardless of the distance to the paramagnetic center, because of the compensation of the T1 with the efficiency of the DMP. And you measure this by doing this epsilon on-off. But then again, when you have an enhancement, then when you turn off the microwaves, I guess you also have to somehow deal with the distribution of this T1 of the nuclei, which, although, you know, these are quadruples, I guess you assume that they are all dominated by paramagnetic relaxation. And so how do you do that? You go for very long recycle delays, or you measure the enhancement as a function of different I mean, because I imagine that some of the nuclei that enhance in the DMP, because they are far from the electron, you don't see them, because when you turn the microwaves off, the T1 is just too long.
Yeah, absolutely. So I mean, well, actually, we never turn the microwave off. Like we're continuously irradiating, but it's still true that the relaxation time depends strongly on the distance. But we always measure the relaxation behavior. So and we get this very pronounced stretched exponential recovery curve. So this is what you would expect from paramagnetic relaxation in the absence of spin diffusion, because you have a distribution of distances, which gives you a distribution of relaxation times, and if you add them all up, they turn out to behave like a stretch exponential. So meaning that there are nuclei, if we want to wait, let's say 99% of recovery of the nuclei to recover, that would be prohibitively long times in some cases. Yeah.
I see. So the other thing that I mean, people that do DMP usually see, you know, shifts of some of the species that are closest to the electrons. So, you know, you have hyperfine coupling. Say if you have protons in your polarizing radical, you'd have hyperfine couplings that are quite strong. And these protons are very important in polarizing the rest of the nuclei. And when you change your concentrations between 0 and 1 in the magnesium manganese system, the lithium, I mean, maybe it's the way it was plotted, but the lithium-6 seemed to be, you know, nailed pretty much at 0.
Yeah, okay. Yeah, it's because I wanted to capture also the spinning side bands, but no, we have a shift of about 80 ppm due to the fermi contact shift. Okay. So here you can see at some point there are, depending on how many manganese are next to it, there are different sides. They are fermi contact shifted. Yeah.
And are these special lithium in the sense of, you know, like there are special protons that are hyperfine coupled to the electron, and you know they are like a conduct of the hyperpolarization to the other protons? I have the impression that everything here is based on dipolar couplings, right?
Yeah. So basically, when we only get large DMP enhancement when we have slow electron relaxation times. And in this case, the T2 relaxation time becomes very short because of the BPP plot. But so longer the correlation time, the shorter the T2. So this means that for electron spins that are good for DNP enhancement, we cannot see the nearest neighbors because they have just such a short T2. But in any case, I mean, what I was trying to say is that because spin diffusion for lithium-6 and certainly for oxygen-17 or yttrium-89 doesn't play a role. So it's just about direct polarization.
So if I could follow up on Lucio's first question, maybe you answered this earlier and I missed it, but you just said you can ignore spin diffusion. And why is that?
Well, I mean, maybe not ignore, but I mean, the spin diffusion efficiency will depend on the strength of the interaction, right, of the nuclei that we are looking at. So we try to quantify how much the spin diffusion affects the overall buildup of the magnetization, and we did that just by looking at the buildup curves in a saturation recovery experiment, and we saw this markedly stretched exponential behavior. So the curves were relaxing with a stretch exponential factor of beta about 0.5, and this is something that is known from the old days, from Blumberger and so on, that when spin diffusion is efficient, you have a common spin temperature throughout the system. So all spins tend to relax together, and in this case you get a mono exponential relaxation behavior. But while when spin diffusion does not play a role, then you get this distribution of relaxation times that turn out to look as a stretch exponential. And so, I mean, for lithium-6, we might be in some kind of intermediate case, because I believe that to some extent there will be some spin diffusion and direct polarization will also happen, even to far away nucleus. But for yttrium-89 and for natural abundance oxygen-17, I think it's pretty fair to just estimate it, to just think that there won't be any efficient spin diffusion. So for example, yttrium-89, we were looking at nearest neighbors, and the strongest possible dipole coupling is something like 5 Hertz, and we are spinning at 10 kilohertz. So I think there is no contribution from spin diffusion in that case.
Clara, you had the question.
Yeah, just so I apologize, I was a bit late. So just following on the spin diffusion then, so what did the lithium-6 and the phosphorus look like in the manganese phosphate thing? Did you
in terms of
the enhancement and the
yeah, so yeah, in terms of enhancement, I think we didn't look at phosphorus 31, but in terms of relaxation, let me see if I have the figures.
And also following on, okay.
I was hoping to maybe it's not here. So yeah, for in terms of this stretch relaxation behavior, we saw that for lithium-7 and phosphorus 31, we had single exponential relaxation behavior. So in this case, the spin diffusion was really equilibrating the polarization throughout the entire sample. While for lithium-6, we had
that's what I was imagining. And so in any of these cases, did you see examples where you, in the DNP, you found a regime where you selectively enhanced one of the local environments more than others? I mean, in cases where you maybe had...
Not on purpose, but we had, for instance, cases where we had some agglomerations of metal ions. And in these regions, metal ions that are in a more clustered region, their electron relaxation time would drop, but the nuclear relaxation time would be fast because they are in closer proximity. And for these cases, we could really see, if we were on the negative side of the DNP enhancement, we could see at the beginning a positive growth of the magnetization in a saturation recovery, because those nuclei relax fast but are not DNP enhanced, and then it dropped to a negative side because the nuclei that are in the regions where metal ions are less
That's really nice. And did you ever see, you know, some of the lithium DNP stuff we've been doing where we've looked at the enhancement of the junk on the surface? Did you ever see any evidence of polarization from the manganese to any any junk or carbonates on the surface, like any of the 0 ppm peaks? You know, was there any evidence for enhancement?
Yeah, so in this work that Shira did, here the idea was to try both things, the DMP from outside in and from inside out, and in both cases she was able to enhance so here the coating of this material was okay. It was possible to get all the, and I mean now the next step would be we want to be more quantitative about this, right? How far are we going outside and how far are we going inside?
So Claire, is junk on the surface the term of art in your papers?
No, I just said if I said the SEI, the solid electrolyte interface.
It's a secret ingredient of the system.
The solid electrolyte interface would be even less of a meaningful term than the junk on the surface. So, but no, the designer surface that we use to passivate the batteries is what I meant to say. So I apologize.
I think Manuel had a question as well.
Thank you.
So I just have a quick question. So can you maybe estimate the maximum number of spins you can polarize with one radical, and does it differ with the different metal ions?
I mean, yeah, this is a question that we are also trying. We are not sure about this. So the question I'm not sure. So in terms of how many nuclei we can, I mean, in principle, I just said we can go infinitely out as long as the paramagnetic relaxation enhancement is the dominating relaxation. But I don't know if, I guess for every polarization step, we need to recharge the electron. So in some, I think there must be a trade-off between number of nuclei that we are polarizing and electron relaxation times. But this is something I'm not sure how we can prove it. And yeah. So or if we ever reach that limit, I think we haven't, but okay. Yeah.
Okay, I think if there are more questions, we can leave them for the after discussion party. So Christian, back to you.
Yeah, so I would like to invite Mark to introduce Manuel for his talk.
Yes, welcome. Hello, everybody from Utrecht. So it's a great pleasure for me to introduce one of my first PhD students. Manuel probably remembers that. Manuel Etzkorn. He studied physics at the University of Göttingen. And then he did a diploma work already at Max Planck. And I think that was already NMR, right, Manuel, if I remember correctly. Yes, the first paper was during the diploma master thesis. And after his PhD in Göttingen, he then went on to work after a short stay with Adam Lange to Gerhard Wagner. I think Gerhard is also here and today present. For a postdoc at Harvard and MIT Harvard Medical Center in Cambridge. And then he moved back to Germany, where he first was a research associate with Henrike Heise at the NMR Center in Jülich, I guess, or Düsseldorf. And then he first was head of the independent Eminator group for 7 years until 2020, I think, where he had a prestigious grant to set up his own group. And since last November, he's head of the independent Heisenberg group. Again, I think a prestigious stipend in Germany. And just very briefly from my side, I think that also just attests to what he just asked. I mean, I was really always impressed with Manuel that he has been extremely broad in terms of magnetic resonance he's doing. So in my lab, he was doing solid-state NMR, membrane proteins, protein folding. And then he went to Gerhard's lab to do solution NMR. And I guess you have seen some of his papers on DMP in cells, which were really very nice. Utopia, the methods development, and the most recent paper, which I guess we'll hear about. So very versatile, very broadly interested. So the floor is yours, Manuel.
Yeah, thank you very much, Mark, for the kind introduction. So hello to everyone around the world. It's really a great pleasure to be part of this wonderful NMR seminar series. And today I would like to present two research areas where I think NMR can really contribute a lot. And this is related to membrane systems and biocatalysis. And in the interest of time, I will just give a brief outline for the membrane systems to have a bit more time for the biocatalysis project. Okay, so if you want to study membrane systems, of course, one of the very central questions or choices you have to make is the choice of the membrane mimetic environment. And there are many choices or many possibilities, and people, including myself, like to argue which of these are more native. And I have a rather strong opinion on this, so I would call none of these really native. So if you are interested in really providing a native environment, you should consider using either whole cells, or if you're just interested in the membranes, also membrane fragments might be interesting. And for some system, you can also solubilize native membranes with suitable polymers. Now, while not really native, I think every single one of these systems has some advantages. And we have been quite interested in the so-called nanodisc system, which basically comprises a lipid bilayer that is basically stabilized by so-called membrane scaffold proteins. And we have basically contributed a few biochemical and also NMR methods to basically increase accessibility of, let us say, a membrane protein that is incorporated into these nanodiscs. And we use these also to understand the effects that an environment can have on these embedded proteins. Then one application of the nanodisc, which I particularly like, because that is really something that NMR is very good at, is basically the combination of nanodisc or the application of nanodiscs to study interactions of proteins or peptides, ideally intrinsically disordered proteins, with the membrane surface. And here, basically, the advantage of using nanodiscs is that you really have a very stable system that is very well defined, very soluble, and so we basically are quite sure that if you add proteins, that it will not destroy your membrane. And we have used these systems, for example, to study the interaction of alpha-synuclein with membranes. And here you can see basically NMR data to identify the binding modes of the alpha-synuclein to the membrane surface, depending on lipid content. So here we produced nanodiscs with different amounts of negatively charged lipids. And you can see, so here's plotted the intensity change in the absence and presence of nanodisc along the sequence of alpha-synuclein. And you can see that if you increase the charge density, you change basically the binding mode of alpha-synuclein to the lipid surface. And now you can directly connect these binding modes also with other biophysical methods, in this case, just regular THT aggregation assays. And you can see, for example, that this binding mode here leads to a strong inhibition of aggregation, whereas binding modes like this can actually accelerate aggregation and probably also induce aggregation. And in a very similar setup, we also studied the EGFR receptor. And here we basically also probe some lipid interactions of this so-called JM domain and identified a network of intracellular modulators of the EGFR signaling, including specific lipids. Now, the last membrane system I would like to talk about today is the melanocortin system. And this is sufficient now for this presentation. If you just pictures at it's a prototypical GPCR system. So here we have a GPCR to different ligands. And basically, we use this system for our long-term goal to develop a strategy that allows high-resolution insights into structure and dynamics of GPCR signaling in what I call a native state. And basically, with native state, I mean using Y-type receptors in an, let's say, intact native eukaryotic cell membrane. And basically, over the last years, we have now established production of the different components of the system, including the GPCR in insect cells. We get nice activity assays, so we're quite confident that we have active receptors. And now, of course, to realize this goal, there are a number of limitations, and they are related, on the one hand, basically to stability, yields, and isotope labeling of the receptor. In particular, basically the combination of low yield and rather expensive isotope labeling strategies in insect cells translates then to the overwhelming limitation of sensitivity in NMR. And basically, the last years, we therefore developed, or first developed, a number of methods that are tailored to overcome these limitations. And one of these is basically the Utopia NMR, which allows acquisition of low gamma, so in this case, 13C spectra or 13C detected spectra for free during the acquisition of conventional proton detected experiments. So here the idea is to use normally not used magnetization and transfer it into useful information. And this works particularly well for large biomolecular systems like membrane proteins. And a second approach is so-called targeted DNP. And here, so this approach basically allows the selective hyperpolarization of the target molecule inside a huge background. And this is, of course, if you then want to go to native membrane, that might be also very helpful. And more recently, we developed in collaboration with Vlado Gelev and Hari Atanari, a method labeling strategy that is basically much cheaper for eukaryotic cells. And this basically solves two problems. So you can basically isotope label your receptor for much less money, let's say, and you gain quite some sensitivity because of this method labeling. This is just an example for a test system where you really get a factor of 10 in sensitivity. Okay, and now how does this strategy look like now for the GPCRs? So we will basically use the insect cell expression to produce our receptors, and we have now also established a new cell line that shows some elevated expression yields. And now to really get a native environment, one approach is to just use the native membrane fragments and then apply our targeted DNP setup. This can give some selective insight, I think, into the receptor ligand interactions. However, the problem here is, of course, because you freeze the sample, you will not get dynamic insights. And because of the rather limited spectral quality of the DNP, you will also get only specific insights. Because of this, we also in parallel now started to use polymer extracted or polymer assisted extraction of native membranes disk. And they actually show quite nice disk that you can also purify. And so basically these are very nice samples for cryo-EM to get information about the structure. And now using our method labeling strategy, we also hope to get NMR insights into the dynamics of the systems. So here, I think the idea is that we really need the method labeling because these disks are quite more heterogeneous and a bit larger than conventional nanograms. So I think we are now in a very nice situation where we have established all our methods, and now we can basically continue to apply these to our GPCR system, and yeah, we're looking forward to see how it really works for these systems. Okay, and with this, I would like now to enter the amazing world of DNA-mediated catalysis. And here we are interested in so-called DNA enzymes. And DNA enzymes are single-stranded DNA sequences that have been identified by in vitro selection. They basically comprise a fixed catalytic core sequence. In this case, this is 15 nucleotides long. And you have two substrate binding arms, which can basically be freely designed to bind a specific RNA target. And what the DNA enzyme can do is it can cleave this RNA. And if you now imagine that this would be an mRNA, of course, cleavage of this mRNA would lead to a suppression of the encoded protein. And this is, of course, highly relevant for the treatment of many different diseases. And what I personally like very much about the system is that it largely simplifies rational drug design. So if you look at the conventional way of designing these drugs, you normally achieve selectivity via the structure of the target protein, for example. But of course, this is a quite long process. You first need to solve the structure of the protein, and then you need to find a drug that binds in these binding sites, for example. And you need to make sure that it only binds to this binding site. And now in the DNA enzyme world, this is largely simplified by going from structure to sequence space. So here, basically, you achieve selectivity just by sequence. And of course, sequence for many targets is already known. So you can basically develop a very selective DNA enzyme within a few minutes. And this, of course, does not only work for mRNA, but it also works for viral RNA and also non-coding RNAs. So in general, you have here a very powerful tool that would, in principle, directly follow successes of the mRNA technology. Now, of course, the big question is, why is it not used already? And here, basically, the reason is that the DNA enzymes experience a very strong drop of activity in going from in vitro systems to cellular conditions. And basically, our working hypothesis is that to overcome these limitations, one really needs to first understand how these DNA enzymes work on a molecular level. And this is basically what we set out to do. Following, I would like to present our results that we could obtain in the last years in the system. So let's have a closer look at our sample. So here's our DNA enzyme shown in red. And this is a DNA enzyme that is designed to target the mRNA of the prion protein, or fragment of the prion protein. And one important information to know about these DNA enzymes is that they are only active, or they only cleave their substrate in the presence of divalent metal ions. And here we have a thread-based activity assay where we can see that the assay works in a way that we have a fluorophore on one end of the substrate and the RNA and a quencher on the other end. And then basically you can monitor complex formation, and you can see that you have stable complexes in the absence of, here in this case, magnesium. And if you add magnesium, basically substrate will be cleaved and you will see an increase in fluorescence. So basically that means you can get stable complexes in the absence of divalent metal ions. And this is what we used then for first NMR characterization. And so this is basically homonuclear correlations of these DNA RNA complex in the absence of divalent metal ions. And you can see that the spectral quality is quite good. And following, I would just focus on this region here, which we call fingerprint region, because it's nicely dispersed and it basically nicely separates in peaks from the arm region and from the catalytic loop region. And of course, since magnesium plays a critical role in activity, it would be nice to also investigate the complex in the presence of magnesium. And to realize this, you can stabilize the complex by just substituting the 2' position with fluorine. And we can show that this basically is not achievable anymore. And you see in the NMR data that it also only directly affects the surrounding of this substitution, and it does not affect the overall structure of the complex. Okay, so basically, the first question we had is whether the DNA zyme actually does adopt a defined fold, or in particular the loop region, or if it just transiently comes into an active conformation. And one easy way to just probe hydrogen bonds is to look at these NOE cross peaks between these protons here. And they will be much stronger in the case the cytosine forms a hydrogen bond, which is Watson-Crick base pairing. And basically we see all peaks for all cytosines in the binding arm region. So basically confirming the approach. But we do not see any additional peak for the cytosines in the loop region. So basically, we don't have any indication for stable hydrogen bond formation. So then we thought, okay, if it is maybe fully unstructured, it should show strongly increased dynamics in the fast time regime. And therefore, we recorded T1 and TET-NOE experiments. And you can basically see here that you you see fluctuations, but it's not like you have a strong increase in dynamics in the loop region. So there might be some structure in this region. And now to probe if we have structure there, we exploited basically the melting behavior of nucleic acid systems. So here we recorded a temperature series. We plot now the peak intensity over temperature. And you see if you have a single-stranded DNA, this just increases, which would be consistent with an increase in the tumbling rate. And now, if you look at the complex and you look at the nucleotides in the binding arm region, you see that you have a clear drop here, which is kind of the melting of the Watson-Crick base pairing, which then has some exchange which leads to peak decrease. So basically, this we can use as a measure for some residual structure. Now, if you look at the several peaks in the loop region, you see that in the central cleavage site area, we also apparently have some structure. And in some parts of the loop also, but in other parts of the loop, it appears that there's not much structure. And basically motivated by this, we set out to update the, let's say, 20-year-old low-resolution model of these complexes, and basically putting in quite some work and combining conventional methods with some new ideas. We could solve now the 3D structure of the precatalytic complex. And this is quite an interesting fold. So we see that one arm region here goes in, and then the loop actually folds back and does an additional turn around the substrate. So this is not like here, it doesn't sit on top, but it really goes once around and then comes back to the other arm. This is a quite fascinating structure, because this basically, on the one hand, aligns the substrate, and on the other side, exposes the cleavage site to some of these nucleotides. And if you look at the structural ensemble, you see that as the substrate is quite well defined, whereas parts of the loop are not well defined. Or let's say sample larger conformational space. And now to evaluate if this is an artifact of not enough NMR restraints, or if it's an intrinsic feature of the system, we turned to Holger Goldke for some MD simulations, and they did several microsecond long MD simulations using different starting structures. And here you can see the root mean square fluctuations over time. And basically what this tells you is that this basic cleavage site area is quite well defined. So this is quite in line with our NMR ensemble, whereas the loop apparently does some fluctuations that would also be in line with the RMSD we see in the NMR ensemble. Okay, now, of course, we also wanted to study the interactions with magnesium, and therefore we did a standard magnesium titration. And you see some peaks that nicely shift and some which don't. And if you now plot these on all resolved protons in our system, it's not so easy to identify binding sites, and the reasons, of course, that the binding will also change the structure. So you cannot really distinguish between binding and structural changes. Therefore, we now use the paramagnetic properties of manganese. And we use the setup where we have magnesium in excess over manganese, so that adding the manganese does not change the structure. This you can see by the absence of chemical shift perturbations. And so basically this titration only leads to peak decreases. And if you plot now the PRE rates, you can identify nice regions that are likely the binding sites of these metal ions. If you plot it on the 3D structure, you can identify 3 binding regions. And using a number of additional techniques, we could also figure out what these regions actually do. So basically, we know now that binding site 1 is required to condense the structure, and basically here you need the metal ions to counteract the repulsion of the phosphate backbones. Binding site 2 basically activates or does a conformational switch that activates the system. And binding site 3 is probably directly involved or indirectly involved in catalysis. And we also had a look at different states with NMRs. It's quite feasible using just recording spectra of the additional states, so single-stranded DNA, and also the post-catalytic state. I will just skip this in the interest of time. Now, of course, the interesting question is if you can also follow the catalysis reaction in real time. And the answer is yes, we can. So if you have your system ready and just add magnesium and record or start recording the NMR data, you can really nicely see the transition occurring during the time course of 1 to 2 hours. And if you analyze the data in more detail, you will see that actually already the first spectrum, recorded a few minutes after addition of magnesium, contains all the chemical shift perturbations. And then this transition we see, the slow transition, basically starts from this conformation. It just changes the peak intensity. And if you now compare this with the magnesium equilibrated state using the stabilized substrate, you see that this first spectrum resembles the magnesium equilibrated state. So that means that reaching the magnesium equilibration thus is not a rate limiting step of catalysis. Yeah, and we also did 2D analysis. So we recorded a number of 2D spectra during this to get more detailed insights. And we decided to encode the kinetic information in one single 2D experiment. And this leads to this characteristic peak-shaped distortions, where the educt state gets increased line width and the product state gets these nice prominent negative shoulders. And then you can basically extract the kinetic information by simulating these peak shapes. And this is what we did. And to simulate this depending on different rate constants. And basically the minimum here would be the best fit condition. And you see that most spins, most resolved spins have rather similar rates, whereas some have some faster rates. If you plot now these faster rates onto the 3D structure, you see that these are really the spins that are directly surrounding the cleavage site. So basically here, NMR is capable of distinguishing cleavage and probably subsequent rearrangement of the loop. Yeah, and this is, we could basically come up with a number of additional states in the catalysis process. We could also develop the most plausible population profile during transition, identifying also rate limiting steps. And basically, in summary, we have solved the structure of this precatalytic complex, got some idea about the plasticity of this system, identified the binding sites for metal ions, identified a number of transient states that might be rate limiting, which of course now is quite interesting from a fundamental aspect. And we then also tried to make use of this by addressing the rather slow catalytic activity of the system. So we were wondering if we can now overcome or improve some of these, or improve the rate limiting step basically. And because of time, I'll make it short. So using ND snapshots, we can basically identify that this nucleotide is essential for catalysis. And we can then basically, based on all of these, our NMR data, or at least speculate that the magnesium binding to this nucleotide is actually detrimental for catalysis. We then designed a new variant, replaced this oxygen group, this oxygen with a sulfur, and basically this largely reduces affinity for magnesium. And we could show that this variant is actually indeed much more active. So this is basically the first rationally designed or structure-based designs of improved DNA design. Okay, and with this, I would like to thank the people who actually did the work, in particular Jan Borggrave, Julian and Aldino for the work on the DNA design project, and basically all others for the work on the membrane systems, also Aldino and Thibault for the NMR methods development. And I would like to thank our local collaboration partners, particularly Dieter Wilbold and Enrique Heise, for the nice support of our research. The EPR measurements of the DNA design were carried out by Olaf Schiemann in Bonn. We get the polymers for our membrane extraction from Sandra Keller. The method labeling was a nice collaboration with Harvey and Flado. I would like to thank all of you for listening. Thank you.
Yeah, thank you very much for the talk, Manuel. Great talk, and I'm sorry that my camera is not working. I apologize for this. I tried to fix it, but I wanted not to miss much from your talk, so I'm afraid we have to leave it like this. Are there questions for Manuel? Maybe I can start. So I was really impressed with your work on the GPCR from the first part of your talk. And you mentioned that you wanted to combine maybe DLP and solutions to NMR. But in principle, you could also use solid state NMR at higher temperatures, right? If you would use, for example, these disk preparations and try to do solid state NMR at higher temperatures, so to say. Yeah. Have you thought about this, or do you think that would be not possible because of sensitivity issues? In principle, method labeling would also work in solid, of course.
Yeah, of course, that would be an option. So we need to see which technique will really give the best sensitivity. So I basically totally agree that sensitivity will be the limiting factor, and DNP is of course a way to largely improve this, and there we need to freeze. But also, of course, proton detected solid state NMR. There I'm a bit afraid of filling the sample into these tiny rotors, but yeah, this is something we, of course.
Yeah, you have a 1.2, so maybe you should try.
Yeah, we will definitely do this.
Yes, I have the, let's see, I have the chat open. Other questions? Otherwise, I will just continue. I don't see. Oh, Christian has a question.
Yeah, I just was wondering, I mean, the target point is a phosphate group, I guess, for the cleavage of the RNA. And I remember from my old times that there were various mechanisms. I mean, I don't even remember the names anymore, but one from the backside, one from the front or so. So what is the mechanism for this enzyme?
Can you see the slide? So this is basically the idea of what's happening. So you need basically a branched base that attacks this proton here and abstracts as a proton here. And then you have basically a transition. And what is happening is that this covalent bond here is then broken, basically.
And I mean, now this is a kind of a generic mechanism. So what is now here the base in the reaction or in your complex?
Yeah, so that's basically yeah, it's a big question. And so the disadvantage, I have to say, of the NMR sample is, of course, that it's highly flexible and it's not really locked in an active conformation. So that means it's not like an X-ray structure where we really know, okay, this group now attacks this point. But we know then from MD simulations that here we have yeah, basically the base region of this G14. That is the one which comes in closest contact to this group here.
Mm-hmm.
What also needs to happen is that this line here indicates so-called inline attack conformation.
Mm-hmm.
And this is, yeah, I think we see also in MD simulations that this is populated to some extent. And basically, if this conformation is present and this group comes close here, then that is what we speculate happens, induces the cleavage of them.
Mm-hmm. I saw that you had a thiophosphate also, which then had a higher turnover or higher rate. And is that somehow plausible then also from this?
Yeah. So basically, if you go back in literature, basically people speculate if this is a metal ion, the base here, or if it's a nucleotide. And our data, or the MD data in particular, indicates that it's more likely the nucleotide. Our NMR data sees that we have magnesium binding also to this region. And so we basically speculate that the magnesium binding actually leads to an inactive conformation here. And that's why we then substituted the oxygen to sulfur. And this reduces the affinity for magnesium. So basically, and this then indeed led to an increased cleavage rate. So basically, we speculate that we remove detrimental interactions.
You needed magnesium for the catalysis, right? So that
we need magnesium to stabilize the loop in an active conformation. So it's not clear if it's directly involved in the catalysis, but it's needed to stabilize the active conformation.
Okay, thanks a lot.
I'll answer the question. Art. I can't hear you. At least I cannot hear you.
I apologize. I got distracted by an emergency email right at the end of your talk. So maybe you already said this, but what's the cause then of the low activity in cells? Is it lifetime of the species, of access to substrate?
Yeah, so that's of course a very good question, and I did not address this. Yeah, so there are also speculations, and most likely what is happening is that, and this is also confirmed by our data, the affinity for magnesium binding is very low so it's in the millimolar range. And what is likely to happen is that other magnesium binders in the cell outcompete. So basically the total magnesium concentration in the cell is apparently sufficient for a catalysis. However, like for in particular ATP concentrations and so on will compete for the free available magnesium. And basically that is something that is postulated to slow down the catalysis in the cell, because just you don't have enough free magnesium. And of course, that is something we would like to address now, to basically increase magnesium affinities at some point.
Maybe I can follow up on this. I mean, wouldn't NMR not be the way to actually investigate that using cell lysates or something? What's actually happening in?
Yeah, so that is, of course, also a good question. So we have started now with fluorine NMR to approach in-cell investigations of DNA enzymes in cells, yes.
Very nice. And then in principle, if that is not working, you could think about some other ligand or something that is not endogenous in the cell, or is that too far to go then?
Yeah, I mean, so basically we already could show that our, I mean, it's not published, but our TIO modification is also more active than the wild type in the presence of ATP. So that might already help a bit, but we need to further increase.
And does also the viscosity play a role, apart from the concentration aspect? That you could,
I mean, there are studies of using crowding, also molecular crowding. It's not so clear, I think. Could be, yes.
Yes. Okay. Thank you. Any other questions for Manuel? Q&As. Okay, there's a question from Christoph Kreutz. Did you try to use aminoproton resonances to follow the catalytic reaction?
What was it? Amino what?
Immunoproton resonances to follow the catalytic reaction.
Yeah, so we looked also at this, but they are not so well resolved. So what we did is we did not change pH, and we wanted to measure at 37 degrees, and then the immuno peaks are quite weak. I mean, so we could not really get very useful information out of this. Yeah.
There's a question from Grace Yopa. Does the loop get stabilized in the presence of any binding partners? Have you tested any?
The loop is I mean, so magnesium stabilizes the loop, that we know. But we have not tested libraries of, let's say, small molecules or so.
Okay. Art has another question, or?
No? Oh, no, I just forgot to lower my hand.
Okay. Okay,
I'm happy to ask another question. Just out of curiosity, how does the rate of this DNA enzyme compare to, say, a protein ribonuclease?
So it's much weaker. So basically, so there are like protein enzymes are much faster in rate. And so basically, if you're now asking what's the advantage of using DNA enzymes over, let's say, siRNA, so I think the advantage is really that it is a self-sufficient catalyst. And
basically, I was just wondering how many orders of magnitude of improvement you could hope for.
I mean, there's, I mean, protein enzymes are in the diffusion limit, right? So there's much possibility. At least 3-4 orders of magnitude should be possible, I think.
Christian, you have another question?
Yeah, maybe just following up on that also a little bit. I mean, these days, of course, RNA is very successful for vaccines, and there are, of course, also ribozymes which could also do the job. So, could you mention something there? And I mean, what about the cellular stability of DNA, which is, I mean, RNA, I mean, it seems that for the messenger RNA, the big vaccines, the big breakthrough was to kind of make it appear not a viral RNA, such that it would be directly destroyed by the cell. And I'm just not biologist enough in order to know whether this happens also to kind of foreign DNA, and whether one could potentially modify it such that it would not be recognized. Is that an issue somehow?
Yeah, so I mean, so if you're compare, let's say, unmodified RNA with unmodified DNA, then DNA is much more stable in a cellular environment. And of course, you have a lot of stabilization possibilities for RNA, and most of them also work for DNA. So there are publications where you have lifetimes of weeks for DNA enzymes that are stabilized. Yeah. And I think it's also nice. So you have a lot of different possibilities. So I think you can tune the lifetime with between several hours to several days at least, which might be interesting later on.